Thank you everyone for being here. Let's get this started. Thank you for everyone being on the chat as well. So if my clicker works, when we talk about serverless, we generally talk about building web APIs. We talk about building workers in the background, processing jobs. We talk about integrations between systems. Maybe we create pipelines that can connect different systems. Or maybe we create step functions and we use Lambda as a unit of compute inside step functions. But today I want to try to explore a little bit of a different use case where using Lambda, I think, is still a bit of a novelty. So we're going to try to see if serverless is a good option for high performance computing. And if you have ever done high performance computing, you know that it's something that traditionally and still today mostly happens on premise. And you have these big clusters with lots of machines using some tool like maybe Spark to distribute computation and run it either on premise or in the cloud. In the cloud, there is also tools like parallel clusters, but very rarely you will see people going for a serverless approach when we talk about high performance computing. And today I want to explore a use case that I had the pleasure to work with where we actually ended up using serverless for a high performance computing use case in the financial industry and the different pros and cons that we figured out, and the whole story on how we built the first prototype, what worked, what didn't work, and eventually what we didn't end up with in production. So let me introduce myself. My name is Luciano. I work as a senior architect for a company called Fortiorem. More on that in a second. I have a few different badges there, but probably the most relevant for this conference is that I am an AWS serverless hero. And one of the things that I'm mostly proud about, which is totally irrelevant for this talk, is this book called Node.js Design Patterns. So if you are into Node.js, check it out. I'd really appreciate feedback if you end up reading it. And you can connect with me on all these different social channels. I'm generally very active, so don't be shy. I'd love to have a conversations even in the next few days. About Fortiorem, we are a service company. We are effectively a consulting company. We are focused on AWS and serverless. So basically, we help other companies to go to the cloud, or if they are already in the cloud, we help them to optimize their workloads. So we have been doing tons of cloud migrations. We also do training and cloud enablement. We have been building high-performance serverless applications, which is what we are going to be talking about today. And also, more recently, we are helping some of our customers to reduce their cloud bills. So if anything like this is interesting to you, or if you're interested in working with Fortiorem, let me know and let's have a chat after this. And one of the things that I'm really proud about in Fortiorem is that we spend a lot of time working on open source project and delivering content, trying to share as much as possible what we learn in the space of serverless and AWS. And what we have been doing consistently for the last year and a half is a weekly podcast where every week we discuss a new topic. It's generally about 20 minutes to half an hour. And in this particular episode, for instance, we do a review of Application Composer. So if you like podcast or video podcast, check out the link. And again, any feedback is more than appreciated. Okay, let's get started. I'm not going to promote anything else anymore. Let's get to the meat. So I have all the slides already online. You can scan the QR code or go to the link there. The reason why I like to share the slides early is because I'm going to provide a lot of links and architecture diagrams. So if there is anything that you will find interesting, you can check it out after this talk. Now I'm going to move on, but the QR code is still there for the next few slides, so you can still get the slides if you want. So today what I want to cover is two topics. The first one is a little bit of an introduction about cloud migrations and the most common techniques on how do we approach cloud migrations. And then we are going to start to explore this particular case study. So we are going to be discussing what's the problem space, what kind of requirements there were, the original implementation on premise, how did we build the first prototype, how did we end up in production, and then at the end, some of the challenges that we hit and how we fixed them. Okay, let's talk about cloud migrations. There is a really interesting framework called the 6 R's of cloud migrations that you can use to start to think, I want to move something from on-premise to the cloud. What kind of options should I think about in terms of architecture? What kind of strategy should I put in place? And generally, these are divided in two groups. Here we have the first row and the second row. The first row is generally the easy choices, while the second row is a little bit more involved and you need to do a little bit more planning to actually do that kind of migration. So let's start with the first one. The first one is retire, which is the simplest strategy ever. You have to go to the cloud and you say, this particular piece of software, we just get rid of it and we don't use it anymore. So this is the simplest one. You just delete all the code and move on. The second one is retain, which is somewhat similar. You basically say, okay, I'm going to the cloud. There is an entire company-wide strategy where I'm moving a lot of stuff to the cloud, but some parts of the software still remain on-premise. So retain means you leave some stuff on-premise, and that also means that you need to have an hybrid strategy where for the foreseeable future, you're still going to be running something on-premise and something on the cloud. Then we have rehost. Rehost is actually, you finally are deciding to move something to the cloud, but you try to do that in the easiest possible way. This generally means that you have a VM, like a virtual machine running on-premise. So you take that same VM and you move it to AWS or some other cloud provider. And of course, this is good because it kind of helps you to move forward to the cloud, but at the same time, you are not really getting any benefit from the cloud because you have the same VM running on-premise or in the cloud. Then we have, to the more involved steps, we have replatform, which is very similar to rehost. So mostly you are working with virtual machines, but this time you decide, okay, I'm going to the cloud. Let me start to take some of the advantages that we can get from the cloud. So it basically means you, for instance, can start to use load balancers, put them in front of your virtual machines. You can start to use auto-scaling groups. So if you get more traffic, you can instantiate multiple instances of that virtual machine, and you can get that kind of automatic elasticity, which is one of the benefits that you get from the cloud. Then the next strategy, and the one that we are going to be covering today, is the most complicated, is refactor. And the idea here is, I have this software running on-premise. I want to run it in the cloud, but I want to do a very big exercise where I want to try to imagine, what if I could rewrite this entire software in a way that is cloud first? So trying to think, what are all the advantages that we want to get from the cloud, and what do we need to do from an architecture perspective to actually have some piece of software that takes all these advantages. And this can take sometimes years. So of course, it's an important strategy, but it's something you need to plan carefully and understand what is going to be the cost-benefit equation there. Finally, the last one is repurchase. Repurchase is more the idea that if there is a software already in the cloud, maybe something as a service that does exactly what my software on-premise does, maybe I don't need to rebuild anything. I'm just going to scrap my own software and buy that particular service. Okay, now that you know all the strategies, keep in mind that in this particular scenario, we decided to go for a refactor decision, and hopefully it's going to be obvious why we picked that particular approach. Now, let me introduce the customer that we work with. How many of you know the field of reinsurance? That's good. I didn't know either before working with them, so I'm going to try to explain my understanding of it, which might not be entirely accurate. The way I like to see reinsurance is basically an insurance for insurances. So you can imagine it's kind of higher level than insurances that we normally deal with. So as consumers, generally you don't get to see the reinsurers. But these are companies that are moving a lot of money because they are effectively aggregating multiple insurances. And the idea is that there are events, for instance, if you take an earthquake or an hurricane, where if that event actually happens, the damage is going to be so big that one single insurance is not going to have enough capital to cover everything. So the idea there is, if you take multiple insurances and they all start to split that particular risk, then even if that event happens, every single insurance is going to lose a little bit of their capital, but they are going to be able together to cover whatever is the amount that was insured. So Renaissance Re works in this particular space. And you can imagine that in this space, you need to track a portfolio where you have all these deals where it's not just two parties being involved, somebody insuring something and the insurance providing the service, but it's actually, there is an entire tree there of different parties being involved and the risk being splitted over and over. So if you take the entire portfolio, it's effectively a big graph, and you need to track that particular graph and understand how it evolves over time. And technology for this kind of companies is fundamental, because if they cannot track what's going on with their own portfolio, they cannot decide, do we buy more risk? Should we sell some of the risk? And that's something that they have to do every day to keep the business profitable and keep growing their customer base. So this particular company had two workloads that are very similar to each other. The first one is called risk rollup. And the idea of risk rollup is basically they take this graph that represents all their deals, and every day they run simulations on it to try to understand what could possibly happen. What is the worst case? What is the best case? And based on the output of that particular process, they can decide what is their position in the market, whether they should sell more insurance products, or maybe they should offload some of that risk to other companies. It's something that they had to build in a custom way. So they built it on premise, they built it from scratch with their own technology. So it's a custom model that they kind of imagine, and they have been running for multiple years. And you can consider that an high performance computing type of workload because it processes something in the order of 45 terabytes of data every time you run that workflow. And it can take up to 8 hours, between 6 and 8 hours. So something that you can run once or twice a day, maximum 3 times. Then there is another variation of this workload that is called deal analytics. Here, the use case is similar, but a little bit different. The idea is that if there is somebody, like a broker, that is trying to close a new deal, they might want to simulate what happens if that deal is coming into the portfolio. So they want to simulate kind of a future scenario. And because they're on the phone trying to close the deal with a customer, this is something that needs to run really, really quickly, hopefully in the order of minutes. But it's also a more kind of simplified version of the problem because it doesn't have to simulate everything, but it's just going to simulate a sub portion of the entire portfolio. So something that gets executed quickly and possibly thousands of times per day. Now, this is more or less how the initial solution on-premise was designed. It's a very simple architecture. You have a modeling system on the left side, which was written in Python. And the role of this particular system is to just read all the inputs that are available, which basically define the structure of this graph, understand what needs to be simulated, create a job plan. And this job plan is basically scheduling jobs using RabbitMQ. And then on the other side, we have a cluster, in this case, implemented with Celery. So again, it's still Python code running there that picks up all the jobs, and you have all these machines executing jobs in parallel. There is a network file system to get the inputs and the outputs. And then there is also a Redis, which we will see a little bit more later on. But the idea is that Redis is used to keep some shared state between all the instances in the cluster. Now, what are the challenges? Why this company is deciding that they want to do something different? Because this solution works and has been serving the business for, I think, 15 years. So it is definitely something stable, but now the company wants to try to do something different. And the reason is because there are some problems that today are becoming more of a problem than they used to be maybe 15 years ago. So the company needs to change something. And one of the problems is that it takes too long to execute a job. And these jobs are not always successful. So you can imagine somebody in the morning goes in, kicks the job in, 8 hours later, the job fails. And they're like, okay, what am I going to do now? Am I going to run it again and then spend other 8 hours waiting here? Okay, probably tomorrow I'm going to see some results. And basically they can keep postponing their work from one day to the other, which is of course very bad for the business because it's kind of limiting the kind of decision making that they need to do very fast. The other problem is that there are competing workloads. I mentioned Rollup and deal analytics, this kind of long job, and many, many small and fast jobs. These two kinds of workloads are running on the same platform. So sometimes when you have a big Rollup running, all the deal analytics, the one that needs to be very, very fast, will go much slower because they're basically competing for capacity. So you have somebody on the phone that is expecting a result in 1 or 2 minutes, and maybe this time it takes 20 minutes, which is too long for them to be able to close the deal on the phone. So this is something that for the company has been requiring a lot of coordination. So people literally asking each other, can I actually run this now? Are you finished right now? And you can imagine that, okay, I'm going to go for a coffee and then come back. Oh, you are not finished yet. Okay, let's talk in 1 hour. And you end up wasting a lot of time just trying to coordinate people. And the other problem is that the company is always getting more and more deals, which makes the whole thing more complicated. So the idea is that if the company keeps growing, all these problems are just going to get worse and worse. So how do we position ourselves so that we can keep growing without having to be worried about all these things? So overall, it makes things very complicated. It's difficult also to add new features because there is already so much complexity that nobody wants to touch this thing and add more features. And overall is giving a very high total cost of ownership. So the plan is, we heard that the cloud is great. Maybe if we go to the cloud, we can fix some of these problems. But more realistically, let's try to understand what we want to achieve. And what we want to achieve is better performance, have consistent runtimes. It doesn't matter if I'm running a big rollup and many DL analytics. I should expect consistent performance as if they were running in isolation. And also we want to support more executions more often. So not just 2 or 3 executions per day, but probably more of them. And also we want to position the company in a place where if we increase the business by 15 times, we still have a technology that can support that level of business. So the first goal that we put in our team when we started to work on this project is, let's try to see if we can possibly run a rollup, which today takes from 6 to 8 hours, in just 1 hour by going to the cloud, which was a very ambitious goal, but let's see what happened while trying to do that. So we started to look at our options, and we were interested in seeing what do we use for compute, because we want to do something that is as cloud native as possible. So we should be going for serverless technologies, and our options there for compute were Lambda and Fargate. And we ended up using both, and I'll show you exactly how, but keep in mind that these are the technologies that we picked at this point. And when it came to orchestration, we decided to use SQS and step functions. But overall, what we were looking for was, can we build this solution in a simple way, in a stateless way, and with an event-driven architecture? And this is the first architecture diagram. So this is the first implementation that we came up with. Don't worry too much about the details. I think the 2 main parts are the one on the left, where basically we are understanding the shape of the job graph, which jobs needs to be executed, and we schedule them on an SQS queue. Then on the right side, in this particular first implementation of the solution, we used AWS Batch using containers as the compute engine that basically takes all these jobs and tries to execute them as fast as possible in parallel. And we also added S3, which is basically replacing that network file system that I showed you before that existed on-premise. Now, one thing that was very important is, okay, we might be building something that works as well as the one that works on-premise, but how do we know if it is any better, if it is faster, if it is slower, if there is any kind of bottleneck anywhere? So we decided to introduce observability from the very beginning, which basically meant let's try to measure everything we can possibly measure and get that data so we can do analysis afterward so that we can evaluate if our solution is working well and where there are things that we should be improving. And one of the things that we were really happy with is that if you use CloudWatch, you get a lot of metrics out of the box. You don't really have to configure anything. You just go in CloudWatch and you have the metrics. But of course, there are some metrics that we wished were there, which were not there. So we still needed to create some custom metrics. For instance, we needed to create a metric to keep track of the number of running containers, to keep track of the number of jobs, which ones were successful, which one failed. We also wanted to see, we are allocating a cluster because in this version we are using AWS Batch, so we still have a cluster with EC2 machines running containers. We want to make sure that we utilize the cluster as much as possible. So the CPU utilization hopefully should be as close as possible to 100% in average. And finally, we also introduced detailed timing, so trying to see how much different parts of the job execution were taking, how much time did we spend on I/O, and how much time did we spend in pure CPU computation. One tool that is really cool that we discovered along the way is EMF metrics. I don't know if anyone knows EMF metrics. So generally, when you want to create custom metrics in CloudWatch, you use a particular API that I think is called put metric data. So you have to make that API call and describe what is the new metric that you want to create. Now that API call has a cost and there are a bunch of limits. So it can be sometimes annoying. If you want to create a lot of metrics, you might easily run out of the limits, or it might become very expensive to the point that you decide not to use all the metrics that you need. So EMF actually solved this problem in a very interesting way. It's effectively a logging format. So in your logs, you can produce JSON lines that are conformant to this particular format. And in that JSON line, you are basically describing the shape of the custom metric. Now, what's happening behind the scene is that AWS is basically scraping all your logs, finding these lines and ingesting them as custom metrics. And the best part of it is that all of this stuff is free, and you have much better limits in terms of the amount of metrics that you can ingest. And there is an interesting case study in the AWS blog from FireEye, where they show you that just by switching to this particular approach, they save 65% of the bill in CloudWatch. So if you didn't know that, it's something we discovered and we were very happy with. Now, how well did we do with this first implementation? So we were able to run the rollup in just 1 hour, which was perfect. We already reached our objective, so we were really happy about that. We are running all the compute in AWS batch, which is kind of a managed service, but not really, because you still need to think, I need to pre-allocate a cluster with a certain number of machines, but it was still managed enough that it was a reasonable compromise. And then we started to look at cluster utilization. And if you see in this graph, the green line there is the average of the CPU utilization across all the instances in the cluster. And you can see that here we have moments where we hit 100%, which is great, but we also have moments where we are very close to 0. And then overall, we are probably below 50% in average. So this is not great at all. We are definitely wasting a lot of resources there because we are allocating an entire cluster and we use less than 50% of that capacity. So this is definitely a problem that we should address when we try to go to production. So overall, we thought it was successful as an experiment, but there is more work to be done before we can go to production. So what do we do? What do we need to change to actually go to production and be in a better shape? And the answer is we need actually to figure out what we need to change. We need to ask ourselves, do we really understand the workload? Do we need to spend more time looking at the data and the shape of things and maybe change something, do something that is more bespoke for the specific workload? So let's review this concept of the job graph, because this is very important in practice. You can imagine this is trying to describe how the deals look like. The first line are all the deals that don't really have any dependency, so you can simulate them straight away without having to wait for anything else. You can run all the green blocks there in parallel. The problem is when we go to the next line, you can see by looking at the arrows that certain nodes are dependent on previous nodes, and there are, for instance, nodes here that are dependent even in multiple nodes. So that basically means that before executing this job, you need to wait for all the previous ones to be completed. So there is significant amount of orchestration to be done. And if we don't do this thing correctly, of course, we waste a lot of time waiting for jobs. And unfortunately, that was a simplification, because the reality is even more complicated. In that previous diagram, all the jobs were similar in size, but in reality, that's not the case. And actually, there are some very big jobs that we call pivot points that are basically holding off computation because they have a lot of nodes that are dependent from them, and they will take a lot of time running. So for instance, you can imagine that this job here, if there were a lot of nodes here, all these nodes will need to wait a lot of time for this job to finish. But this job is being executed on one instance alone. So this is the moment where in that previous graph, you saw that we were close to 0% because there was probably only one node doing work while all the others were waiting for this work to be unblocked. So how do we fix this problem? So we started to look at the input data, and the input data, if we simplify a little bit, looks like a CSV file where every record is trying to describe some amount of monetary value. But all these records are not correlated with each other. So when we realized that, we decided, okay, what if we take one job and we actually split it into multiple jobs, much smaller jobs? And we came up with this kind of idea where we try to have kind of a standard unit of compute by creating jobs of the same size. So if a job was too big, we split it into smaller jobs. And that way we ended up with a combination of jobs that were much smaller and more or less of the same size. And the nice thing is that the relationship between the lines in the input files is respected between the subsequent jobs. So basically, we were able to do this strategy, and if we finish only one green slice there, we can immediately start the subsequent slice in the next job. So this is actually a very nice property of the graph that we discovered, and we decided to use it to improve performance, to make things a little bit more consistent. But now there is a new problem, because we started with 1,000 jobs, and we are ending up splitting one single job even into 1,000 pieces. So you can already see that we are now running 1 million or more jobs, which creates new problems, because now there is a lot more coordination needed, and we need to make sure we do that efficiently. So we have this idea. How do we take that idea into production? And let's review a little bit better how the worker is configured in this new version, because at this point, we also decided not to use AWS Batch anymore, but to go for Fargate and Lambda directly. So let's start to understand how we put all of that together. So we still have a queue, and we need to get the jobs from the queue. Then we have a worker, and this worker is the one, in this case, running in Fargate, that has all the modeling code that needs to be executed. So it's going to be reading inputs from S3, execute all the modeling, write the outputs back to S3. But now there is an interesting problem, because all this thing is in a way stateless. One particular worker takes a job, but doesn't know anything about the entire graph, right? So somewhere we need to have a picture for how that graph looks like. We need to understand when things are completed, when things are failing, if the entire execution is actually completed, or if we need to retry something. So how do we capture that information? And we basically managed to create an event-driven system that can give us that information by simply letting the worker there send events into a Kinesis stream. And what kind of events? Events such as, I'm starting a new job, this job is finished, or this job failed. And because we are using Kinesis, Kinesis basically keeps things in order. So literally, by just looking at this stream, you have the entire history of everything that is happening in the cluster when you are running a specific execution. So back to Fargate and Lambda. Why do we have both? Why did we want to use both? So Lambda is probably the coolest thing ever, because the interface is very simple. It spins up instances very, very quickly. You can spin up thousands of instances in the order of seconds. So it is really good for this use case where we have sudden spikes and we want to have as much compute from 0 to the maximum in a very short amount of time. But at the same time, Lambda has limits. For instance, you cannot run a job for more than 15 minutes. If you want a GPU, you don't get a GPU. If you need a lot of local disk space, you don't get disk space. So Fargate is kind of the second best thing. When you need these extra things, you need to do a little bit more work to set up a Fargate container, but then you can do much more with a Fargate container. Although Fargate comes with a problem that if you want to scale from 0 to thousands of instances, it takes too long, and we will see how. How are we doing with time? Okay, I think we still have 10 minutes, right? Okay, I'll keep going. So S3 is also really interesting because I mentioned already that we do input and output from S3, but now because we are doing chunking, it means that we have smaller jobs that are producing new output, but this output alone doesn't make sense. We need to take it and aggregate it together back to the original size. So that means that we are using S3 now even more because we are producing more input outputs. Then we need to aggregate them and rewrite them into S3. So what happened there is that we realized we were doing more than 10,000 operations on S3 per second, which we will see how it creates new interesting problems. So at this point, we have this idea. We want to use Lambda and Fargate. We know how the jobs are structured. We know how we are chunking things. How do we actually start to feed work to do to this cluster? And the interesting thing here is that, again, there is no off-the-shelf product we can use in AWS. So we needed to build our own orchestration logic ourselves. So let's review what is the life cycle of a job. A job pops up in a queue. It gets picked up by a worker. When it's finished, we are going to be sending an event into a Kinesis stream. Now let's try to understand. This is kind of the local view. Let's try to understand how do we get a global view of the entire execution. And I mentioned that we put stuff into this Kinesis stream. So who is using that information? And we have a Lambda here that is called the scheduler Lambda, which is kind of a special Lambda that takes all the data from the Kinesis stream. And what it can do is basically saying, okay, I see that a new job was started. I see that another one was finished. So based on all of these events, I'm going to store all this information in a Redis cluster. So I'm going to make all this information available at the global level. And I can have even multiple instances of this Lambda running in parallel, doing all of this. So basically, we make Redis our source of truth. At any given time, you can look at Redis, and you should see exactly which jobs are scheduled, if they are completed. And you can also understand, and this is the most important bit, this Lambda, when anything is updated, it can also see, oh, this job completed, and actually is unblocking a bunch of jobs that now have completed all of their dependencies, so they are ready to go. So this Lambda is also responsible for scheduling the next line of jobs when they become available. This is why we call it the scheduler Lambda. And basically, this is how we are being able, in a serverless, stateless, event-driven way, to have this local view, but also to keep the global view and make progress at the entire execution level. Now, one other interesting detail here, and I'm going to speed up a little bit in the interest of time. Here, we can start to see that we can run this entire cluster in two different modes. So we can pick between running the jobs in Fargate and running them just in Lambda. And the reason is we have this idea of low priority and high priority. Low priority is the Rollup job, the one that takes up to 8 hours in the old world. Now it takes about 1 hour. And then we have DL analytics, which needs to take minutes, if not seconds. So when we run the Rollup, there are still jobs that can take more than 15 minutes because some of the models are so complicated that even if we do chunking, they can still take a long time. So in that case, we ended up using Fargate. And also, we don't really need to get a result straight away. If it doesn't take 1 hour and takes 1 hour and a half, it's still fine. While here, we really want to be as fast as possible in the order of minutes. So in this case, we can just use Lambda, and Lambda spins up thousands of instances in seconds. Another interesting thing is that here we can get some kind of economy of scale because Fargate at scale is up to 20 times cheaper than Lambda at scale. It means if you do the same exact amount of compute, Fargate is about 20 times cheaper. So here, because we do a lot of compute for hours, this comes also much cheaper than just doing all of that in Lambda. Another interesting detail is that you might be wondering, what if something crashes? And sometimes there are crashes that you don't even have a try catch because maybe you just run out of memory and your process gets killed. So if that would happen and you are not aware of it, you basically stall. You don't know anymore how to progress the entire execution. So of course, we want to avoid that because that will mean that we maybe run 98% of the workload. And then just because something fails in the end, we don't know anymore what to do next to keep progressing. So we realized that we could use Event Bridge. Sorry, my only instance of Event Bridge. Because Event Bridge is actually pretty cool. It can give you the ability to read events for other things that are happening in other AWS services. And one of these events is a container just crashed. So what can we do is just listen to that kind of event, ingest this type of event as part of our history in Kinesis, and then our scheduler can see when there is a failure and maybe reschedule that particular job and try again. So just to summarize what was the outcome at this point, we went to production, we were really happy, but let's make an analysis on how successful this was. In terms of business, we were able to run the rollup in 1 hour, which was our initial objective, so everyone was happy about that. We removed the limits on the number of runs. We can run as many DL analytics as we want-ish, because of course, even in AWS, there are limits at some point, but it wasn't as constrained as it used to be in the premise world. And also it was much more predictable. Now we know that if we run a DL analytics, it doesn't matter if there is only one running or if there are 1,000, they are more or less constant in terms of execution time. So the business is spending more time thinking about what can we do next in terms of business capability, rather than thinking, should we buy more servers because the business is growing? Who needs to provision these servers? When do we need to order them so that they can arrive in time? And all these kind of things that if you have been working with on-premise systems, you probably are familiar with. So now the business is thinking more, we need to grow. What can we do in terms of business to keep growing rather than being worried about the technology? But if we think about technology, one very cool thing that we feel we achieved is that we were able to use serverless successfully for a use case where the industry isn't still there yet. Like you wouldn't find a lot of use cases trying to do something similar. So we were really proud about that. And we think this is something we are going to be seeing more and more. And one effect of that is that we compare the code base of the original solution in premise and the new code base, and the new code base was like 70% smaller in terms of amount of code. And if you take the modeling code, that's pretty much the same code. So basically what we removed was the entire orchestration code that needed to exist on premise, because there is so much more that you need to manage on premise. So that you can imagine that that gives the team a lot more agility. You are more confident about your code. You can keep it in a better shape, and you are not worried to try new things and add new features where needed. So this is increasing team agility. And also, if we want to be a little bit green, because it's a hot topic right now, because we are using serverless, most likely we are in a better position in terms of carbon footprint. I don't really have any numbers, so take that with an asterisk, but I can give you more details if you want to chat later. Okay, now I just want to close this talk with a couple of stories about moments where things went terribly wrong and we didn't really know what to do. And in both cases, it's about, you think that the cloud scales infinitely, but reality is much different. There are limits. And given the scale that we were operating with, we hit some of these limits. So the story is, how did we work around these limits? And the first one is S3 throughput. I told you that we were doing tens of thousands of requests per second. And before working on this project, I was like, S3 scales forever. You can throw as much data to it as you want. They're going to figure it out. It's amazing. It's the best service ever. I never have to worry about that. Then reality was that we were seeing a lot of throttling errors in S3. And because we were seeing all these throttling errors, our workers were stuck. They were not able to do progress because they were waiting either for input or they were trying to write some output, and that operation was failing. So the job simply couldn't be either executed or couldn't be completed. So that basically meant that the entire execution was slowing down and sometimes was even failing because it was retrying so many times that at some point was giving up. So that was not good. And the reason why this happens is because the way S3 works is that they look at your prefixes, all the operations that you do, and they try to identify patterns in your usage cases. So if they see that you are using /example /1, for instance, as the prefix for your objects, if you're using that a lot, eventually they will decide to partition that particular space, allocate it into different servers, and in that way you get much more throughput. But all of that stuff is done automatically, and for our use case, their own algorithms didn't work well. And in reality, it's because we were doing very spiky things. So when you run an execution, it goes very quickly from 0 to 10,000. And then you end up on a weekend where there are 2 or 3 days when nothing happens. So at that point, S3 was scaling down everything again. And then the next Monday, you come back, you run an execution, and you get a bunch of throttling again. So there is really no out-of-the-box solution for this. Like there is not you can do yourself to try to fix this problem. So the only thing we could do is reach out to support and ask them, we are bumping into this limit. What else can we do? So we described this use case, and they effectively confirmed this story where the automatic algorithm didn't work well enough for us. So they were able to configure for us a bespoke partitioning scheme that is already pre-organized for the moments where we need to reach 10,000 requests per second. And that's basically how we fixed that problem. So long story short, when you have this kind of problems, make sure to talk with support. Support is generally very, very helpful, especially in these cases where you are hitting the limits, because it means you are spending a lot of money on AWS. So they are really happy to help you out. Then another quick one, and this is the last one I'm going to show you today, was scaling Fargate containers. So we wanted to go from 0 to 3,000 containers as soon as possible in Fargate. And with the first iteration, that was taking more than 1 hour, just instantiating 3,000 containers. So we were already wasting 1 hour just spinning up containers, even before doing the computation. So that was not acceptable. And the reason why this happens is because in Fargate, you have 2 ways of running containers. One is you define a service, which is effectively like a blueprint for how do you want to run containers. And then you say, I want 1 instance, so 1 container running for this service. And at some point, you can tune that to 3,000. And at that point, the system is going to automatically try to allocate more containers to meet your request. The other approach is when you call the run task API directly, And the run task API is basically, you don't think in terms of services, you just say, this is the specification for a container, just run this one container as it is. So we realized that using the service solution and just saying run 3,000 of this, AWS was very slow to scale things up. While if we were running run tasks directly multiple times, so 3,000 times in a row, that was much faster, and we were able to spin up 3,000 containers in less than 20 minutes. The problem was that we needed to do all this orchestration ourselves, so we ended up building this step function that is responsible to see how many containers do we have right now? Do we need to spin up more? If we need to spin up more, run task until you get the number that you actually want. Now, this is not necessarily true anymore, because I think reInvent last year, AWS announced a bunch of changes in the way the Fargate Scaler works. And there is an interesting article by Vlad Ionescu that does a bunch of experiments and gives you some numbers. And I think today you can scale up to 10,000 Fargate containers in 10 minutes. So if we were building that solution today, probably we wouldn't bump into this limitation, and we wouldn't need to build our own Fargate Scaler ourselves. So in conclusion, I think we were able to build what we call a serverless supercomputer. So we can do high performance computing on serverless, and this is pretty cool. There were lots of challenges. It was pretty much uncharted territory, so we needed to figure out the solutions to the problems ourselves, but we did it. So I think it's definitely doable. We are seeing other companies doing something similar. There is an interesting use case there. And also AWS themselves, they publish an open source product called HCC Grid, which has a lot of similarities with what we did. The difference is that I think they mostly run things on EKS rather than using Lambda and Fargate, but everything else is pretty much the same, and they have been using in the financial space as well. So you can check out that other project if you want to use something open source that does the same thing, or something similar at least. So our customer is now serverless first. They have been learning AWS throughout this process, and they are investing more to do things in the cloud and increase their level of agility. So that's everything that I have today. I hope it was interesting. And if you have any question, I'll take them now, or you can find me around for the rest of the day and tomorrow as well. Thank you.